Typically, we work as a subcontractor with an architect. The architect comes up with a schematic design, determines where the walls go, what the structure will look like, and then we come in and work with them to determine how to make sure that it performs, depending on soil, wind, earthquake, snow loads, to make sure that it still stays upright, nothing cracks, everything still performs and looks the same way it did after it was built. Certainly a structural engineer should be involved with the design decisions based on the early part of a project, determine what the most cost-effective method is to build the project. Sometimes an architect may want concrete, but if you can achieve the same look with wood and it's a lot cheaper, that's something to consider. If you receive a set of plans, no matter how you get them, whether it be from the internet, from a local design professional, the engineer could look at that set of plans to help make design decisions to determine what's appropriate for that locality. We are out at a project in Houston, and the whole idea here is so we can have a look at the foundation and the concrete, the wood frame, the roof framing, some of the wall framing, and just some of the criteria that goes into those various aspects of this project. And the fact that we do use different materials. Sometimes you need to use steel, sometimes you need to use wood, and it just depends on the project. And we've got a nice project here that has a nice mix of all of those things. The place we usually typically start with a design criteria would be the foundation. Here in Houston, that's one of our largest design concerns because we have extremely expansive clay soils. As such, we try not to support them on a shallow level, especially for a fine architectural product, because you're more likely to get differential movement, which results in the cracking of brittle finishes. Depending on the type of finish on the project, though, different foundation systems may be more appropriate. If you wanted to try and get further out of grade, or there were flood issues, it would probably be more likely to use what we call a pier and beam system, which might be drilled piers with a wood floor system, so then you can get a full crawl space underneath. That's common in many parts of the country. If you lived in the north, you'd probably have a basement or at least a stem wall to make sure your foundation gets below the frost line so you don't have a heave problem. In some places where the soil is very good, you may not even need drilled piers. You could possibly just cast a slab on stable soil. That's not uncommon in parts of Florida, and even some of the parts of Texas where you get away from the expansive clays. Foundations cost a lot of money. People don't always want to spend a lot of money on it because you don't see it. And people don't realize just how active the earth is. And depending on what your rain cycles are, you may not see it for 3 or 4 years or even longer. But then if you suddenly go from a really dry year to a really wet year, your house could move all around. There are different framing systems that perform better from different localities. Some of that is driven by local industry. Some places are much more comfortable using steel than wood, depending on labor force, depending on material, and then also even depending on climate conditions. Here in Houston, we do have a high humidity, but we still use wood frame because we can dry it in, and we have the labor force to do wood. It's the most cost effective. That doesn't mean that it performs the best, depending on what task we're trying to achieve architecturally. We typically do a lot of wood construction. It is the most economical means. It's the means most contractors are familiar with, so it's an appropriate material for many items. In this particular project, for the floor system, we're using wood floor trusses. They're open web, so it allows you to run your mechanical through it, and your plumbing and your electrical, with much easier than using traditional 2x12 construction. The walls are also stick framed. On this project, it's 2x6 framing. 2x6 gives you a stronger wall, of course, than a traditional 2x4. It also gives you more room to put in your utilities. But on many projects, a 2x4 is perfectly sufficient. And of course, it's more green, it's more environmental, and it's cheaper. A lot of times we use more than just wood. We also use steel to accommodate our different framing requirements. Steel tends to be much stiffer than wood and much more flexible with the type of framing you can do. We're using this steel column that's going to be an exposed painted architectural column to actually hang a walkway on the second floor up here. There's no columns out on the walkway, and so we're building a big bent frame that goes up for the full two-story height to support the walkway out here. The steel is much more rigid so that you can actually still put glass windows and nice finishes and everything without any kind of long-term deflection like you would likely to get with wood. This steel piece right here is both structural and architectural. Obviously, a structural engineer left to their own devices isn't going to invent a tripod, but it does look nice, and it is serving structural purposes because we're cantilevering the entire second floor over it, and the tripod shape does give it stability. And of course, the advantage of using steel over any other type of construction for this type of project is the stiffness you can attain at joints. Concrete would be similar, but it's much more costly, and of course, architecturally, it would be difficult to make look good in something like this at any kind of an economic price. Each column does have drilled footings on it to help support the weight of this, because there is a significant amount of weight over the top of the tripod. And again, the footing actually is an under-ream pier that goes down about 12 feet with a 2-foot ring beam below it to make sure we don't get any spread of the tripod. We look at the loads and you know what forces are coming down, that's what we're retained to do, and figure out how to resolve those forces so that nothing moves once you put it in. Because any movement is detrimental to the performance of a structure. Any project will only function as well as its substructure, and that's a combination of good engineering and good building. Because if something is weak, it will move more than it should, or if it's installed improperly, it will move more than it should. And almost all building materials are very brittle. Sheetrock, brick, any movement in sheetrock or brick, you're much more likely to pick up any distress in it, and it will show itself rather quickly. The design criteria for a roof vary probably the most widely across the country. There are different roofs that perform better in different climates, and the engineer could suggest using a steep gable roof instead of a flat roof, or even vice versa to make sure that the project proceeds appropriately and performs well. On roofs, for example, you can use a metal roof. You could use a composition shingle roof, a membrane roof. There's lots of options, and each one may be appropriate for a different style of roof. For example, on a flat roof, composition's not reasonable. You'd have to go with a membrane if you're less than, say, a 312 pitch. And so you need to make sure that the appropriate roof is provided for the appropriate type of structure. Now, when it gets into sloped roofs, metal versus composition versus clay tile versus slate, those are really more of an aesthetic decision. Each one can perform appropriately when installed properly, which again, it's all usually an economic decision regarding cost, aesthetic, performance.